So, our first separations process. We're starting chapter 20, equilibrium stage operations. This chapter is quite general in the sense that everything is discussed here from the perspective of mass balances, and the use of equilibrium relationship is completely general, applies to all separation processes. That said, what this chapter really is the treatment of the first separations process that we're going to be talking about, gas absorption or gas scrubbing, and the purpose is to clean up, get some noxious or chemical or pollutant out of the gas phase. So we want to clean the gas. This chapter, although it's not emphasized as much because it's sort of a follow-on and sort of everything in reverse and can be dealt with more quickly, this chapter is also a chapter on stripping or desorption, which is, conversely, when you're interested in cleaning up a liquid phase, which might have some pollutant in it. So this chapter, chapter 20, is a general introduction to equilibrium stage operations, which is the stage-wise contact I was mentioning in the very first lecture. But what it really is our look at the first separations process we're going to be dealing with, which is gas absorption, gas scrubbing, and as a follow-on, stripping or desorption. We're moving ahead in the book. We skipped several chapters because it's important for you to get your hands on separations as quickly as possible. And so we fast forwarded, skipped over several chapters in the book and gone straight to chapter number 20, where you can do separations right away, right out of the box, and the sooner you do that, the better, and it's just really incredibly fun. But we will go back to those other chapters later. We'll circle back. Okay, all page numbers here refer to the 7th edition of McCabe, Smith, and Harriott, the newest edition. I cannot urge you strongly enough to read pages 643 to 646 once a day for the next 3, 4, hopefully 5 days, because that text is, those pages in particular, are pure literary and scientific genius. I myself see that now in hindsight. There's a lot of nuances which will slip by you, but the more you understand, and as time goes on, if you return to those pages, they will mean more and more to you. So I just can't urge you strongly enough. Just a general note, I will be following, the book, chapter 20, pretty much, but I'm going to diverge a little bit and spend a lot more time talking about single-stage contact than the book does, because that's the fundamental thing that happens in stage-wise contact. You have to understand what happens when you contact, say, a gas phase with a liquid phase in a lot of detail, and so we're going to be a little bit more thorough than that on that than in the book. So let me give you a few examples of gas absorption in actual use, what you might use it for. And if you want some examples, go back in the book, back to page 565. There they're talking about gas absorption from the mass transfer perspective, which we are putting off until later. But just go to that page and you can see a few examples of the actual uses of why you would want to use absorption to clean up a gas phase. Let me give you an obvious example. Supposing we're in a room and somebody was cleaning the windows or cleaning the floor and used a lot of ammonia, and we walk in and it smells of ammonia, and I certainly would not want to be breathing that air with all that ammonia in it. So, how can we clean up, how can we get the ammonia out of the air? We certainly can't take a pair of tiny little tweezers and be tweezing out all the individual ammonia molecules. That's ridiculous. We can't do that. So we would like to get the ammonia out of the air somehow. What's another example? Well, maybe we're making some kind of a biofuel, and we're trying to get, say, carbon dioxide or water out of some natural gas, and you might do that by absorbing the CO2 or the water with an amine. On page 652, a little bit further into this chapter, page 652, example number 1. Is specifically on absorption of acetone from air with a heavy oil. And that's actually, that example is very apropos, because I think we've all had the experience of walking in a shopping mall and going by a salon where they do fancy nails, and you don't even have to go inside, you just walk by the door and you almost fall over from the heavy fumes of basically acetone, nail polish remover. And it really concerns me because the people who work there, they wear masks, but we all know that masks can filter out dust. But I don't know why they do that, because they certainly can't filter out acetone. So I'm actually quite concerned about the people who work there. But I certainly would not want to be breathing all that acetone. And if they had a little absorber tower there, which could absorb the acetone from the air, that would be great. So that's a very mundane example. Actually, in general, absorption is used to clean up gas streams. For example, to get sulfur oxide out of certain streams. It happens all the time in chemical plants that you can't just take contaminated air with some kind of chemical in it and just spew it out into the atmosphere. You have to clean it up. And so that's why gas absorption is used all the time in chemical plants. Okay, so let's talk through this process of how, without using some magic tweezers, you could get a certain solute that you don't like out of an air, say an airstream or gas stream. Okay, so I'll just use letters that are focusing on this example. So let's just assume we have air, A for air, that's contaminated with a solute I that we're interested in this case because we're concerned about it. So I'll call it I. Oftentimes, the chemical species that you're focusing on, the solute, you call it I, that particular one that you're interested in. And so I would like to get the I, the ammonia, out of the air. So how might you do that? Well, one thing you might do is to contact it with water. And this could be in a big drum or in a tank, and you could literally put in some water there, pump in the air that you're trying to clean, shake it up, mix it up, and let it sit for a while. So this is the before picture. You've got the air contaminated with the ammonia I, and you've had the thought to contact it with some water, shake it up, mix it up really good, and then let it sit. So what's the after picture? After you let it sit for a while, it comes to equilibrium. It settles down to be the way it wants to be. What happens afterwards? Or what's the state afterwards? I've got three versions of the after picture here. When you think it through, what's what you really want to achieve? What you want to achieve is that the ammonia, some of it dissolves in the water. Well, that actually happens because ammonia does dissolve in water. And in fact, it sort of wants to dissolve in water as it comes to equilibrium. We'll talk about that a bit later. But so absolutely, some of the ammonia, so that's why I've drawn these I's smaller than this I, which here hopefully is bigger. So some of the I has gone from upstairs to downstairs because ammonia likes to dissolve to a certain extent in water. And if you think about it, that really is absorption. But the water literally absorbs some of the ammonia, I, and so that if you separate these two phases, which is incredibly easy to do because the air is so much lighter, you can just pour down or drain off the water. So by transferring the I, the ammonia from the air to the water, some of it goes, how much we'll figure out, but some of it goes into the water. You've got some of the ammonia out of the air. You've partially cleaned up the air. That is, in a nutshell, is the essence of gas absorption. Now that part of it here. That part of it here is common to all these three pictures. In all cases, the ammonia some of it has been absorbed by the water. Now, this picture here is the most complicated. It allows for two things which happen a little bit. So you'll notice here, I've got a little A here. It's very small. It actually should be very tiny so that you can almost not see it. But some of the air will dissolve in the water. That happens. And in fact, if air didn't dissolve in the water, all fish would die because they wouldn't have, their gills wouldn't get any oxygen. So that absolutely happens. But the dissolved oxygen, air concentration in water is very, very small. And here you want to look in, say, Perry's Chemical Engineer's Handbook, or go to a source that you trust, is reliable from the internet, and look up or use a search term, gas solubility in liquids. And absolutely a certain amount of the air dissolves in the liquid. It's a very, very, very small amount. So that's why this A should be tiny. Almost too small to see. Also, here we've got water. Absolutely, water boils. It boils at 100 degrees. This is probably happening at something close to room temperature. We're way below the boiling point. But so at this much lower temperature, water, certainly not boiling, but it has a small but noticeable vapor pressure, so some of the water will evaporate. So you'll notice here, aside from the main story that's happening, of I going from the gas phase to the liquid phase and being absorbed so that afterwards there's less I, ammonia, in the air that we're trying to clean up. That's what's going on. That's absolutely the idea, the main point of absorption. But this picture is the most general and allows for two phenomena. Tiny bits of say, the air can dissolve in the water, and some of the water will evaporate. Okay, having said all that, this picture we're going to take off the table because the amount of air that dissolves in the water is so tiny that for several digits, several zeros after the decimal point, that we're just it's such a small effect. You're really very, very, very justified in neglecting that. So no more of this picture. I'm going to cut right away to this picture where all the air stays upstairs. There's no little A down here. None of it has dissolved in the liquid because that's just a very, very good approximation to reality. So this is the more complicated of the two pictures that we're actually, or the two calculations that we're actually going to look at. Here, we, aside from the main thing that's happening, that some of the ammonia gets absorbed by the liquid, we're going to allow for some evaporation of the liquid. And again, so that happens to some extent, and it's not truly negligible. So we should, you kind of to be effective as an engineer, you have to have gone through that calculation once in your life so that you understand it, and so that you understand in what sense it's important and in what sense it's not important. So this is the more complicated of the two after pictures we're going to look at. That said, honestly, it really doesn't matter too much for the absorption process for the ammonia to get from here to here, some of it, whether the air is dry or whether the air has some moisture in it. It almost doesn't affect that process at all. And honestly, actually, if on a particular day, I actually couldn't care less if it's 20% humidity or 25% humidity. If it was like 90% humidity, on a hot day, I would probably care about how moist the air is. But it's just not that important. From the perspective of what's really going on and what we're really interested in, the absorption of I. So the calculation that you do most often is this simplest one here, where you pretend, with a lot of justification, that none of the air dissolves in the liquid. That's an incredibly good approximation, but you also neglect the evaporation of the liquid phase, in this case the evaporation of the water. So this happens in real life. In a lot of situations you have a small but significant amount of evaporation of the liquid that you're using to do your absorption, and we're going to deal with this process first so that we understand everything completely, and then we understand why you can neglect it. And so, having gone through that once in our life, which we're going to do in a worked example problem, we're going to cut to this picture. This is a picture that you basically, these are the usual approximations that you make. The usual approximations are that you neglect the fact that some of the gas dissolves in the liquid, which is a great approximation. It's just very accurate, but you also neglect the evaporation, that some of the liquid evaporates into the air. That's small, but not incredibly small. It can be significant and noticeable. But so, and we will see why we cut to this picture. So ultimately, after we've gone through this once in our life, in a worked example, we're always going to assume this picture over here, where the gas phase is just air and ammonia, or gas and I, and the liquid phase is just the absorbing liquid, and I, in this case, water and ammonia. These are the usual, can't spell, approximations. This is what you usually assume because it's just a very reasonable approach to get good results, reasonable answers for gas absorption. Okay, so there's one other thing I want to talk about, and that is how you actually do this calculation, and that's what we'll talk about in a second. Before going any further, we need to go over a bit of theory, which is kind of review on what it means to have equilibrium between the gas phase and the liquid phase. So here I've drawn the more complicated after picture that we're going to deal with, where we, in addition to having I, ammonia say, present in both the gas phase and the liquid phase, but we also allow for some evaporation of water. So whenever you have a component that's present in both phases, gas and liquid, it's called a distributed component. It's distributed in terms of its location, some of it is in the gas phase, and some of it is in the liquid phase. So whenever you have a distributed component and you allow the system to come to equilibrium, which is what we're doing, after shaking this all up, we're letting it settle down and letting it relax to however it wants to be. So for a distributed component, you write down a phase equilibrium relationship, and it might be Rail's law, if Rail's law is valid. And so just by rote, I write down YIP, where YI is the mole fraction of I in the gas phase, YIP, is XI PI sat. XI is the mole fraction of I in the liquid phase times its saturated vapor pressure. I say PI sat of T because the saturated vapor pressure depends on what the temperature is. So here, if we're doing this at room temperature, you'd look up the vapor pressure of I, ammonia, say, at room temperature. So that's Rail's law, and that works for in cases where the liquid solution is an ideal solution. The more general equilibrium relationship, which we know and love from thermodynamics, is YIP is XI gamma I PI sat, and that means that we allow for non-ideality of the liquid solution and put in this activity coefficient here. A lot of absorption processes occur with relatively dilute solutions, which means that Xi and Yi are quite small. If the concentration of I is a small number, like 0.01, then the activity coefficient is pretty much its value at what's called infinite dilution, at low concentrations. In other words, if you just calculate or plot the activity coefficient and let Xi get smaller and smaller, it just settles down to some limiting value, and that's called the infinite dilution activity coefficient, and this is just a constant at whatever the temperature is. So at low concentrations, you can replace the activity coefficient, which generally depends on composition, with its infinite dilution value, infinite dilution, and so this is just a number. And so now, if I just box this in, which I did in red, you come up with YIP is Xi times some other number, but it's just a number. It's not exactly PI sat, as in Rail's law. It's PI sat, but modified by the infinite dilution activity coefficient. But this is just some number, and we could call it Ki. So at low concentrations of I, which happens a lot in absorber problems, we have YIP is Xi Ki, and we recognize that as Henry's law. So we all have heard of Henry's law, but I just wanted to say this to point out that when you look up a Henry's law constant for distribution of any solute I, for example, ammonia, between air and water, what that Henry's law constant actually is the infinite dilution activity coefficient, which accounts for non-ideality, times the saturated vapor pressure of I. So that's really the meaning of the Henry's law constant. And I'll just point out, clearly the Henry's law constant has the same units as pressure, so it could be atmospheres or millimeters or mercury or what have you. So this kind of relationship, if you look out and the solution of I in the liquid phase is ideal, then you can just use Rail's law, look up or calculate the saturated vapor pressure. If it's not an ideal solution, which is actually true for ammonia and water is not an ideal solution, then you need to look up Henry's law. But, so because I is distributed between the gas phase and the liquid phase, your analysis is going to have to include the relationship for the equilibrium of I between these two phases. So when I is present in both phases, when it's a distributed component, you need to write down the equilibrium relationship for it, and that is either Rail's law or Henry's law, and here they are. So that applies to the simplest picture, where you only have I going from the gas phase to the liquid phase, and it also clearly also applies to the more complicated picture when water also evaporates. In that scenario where water also evaporates, water is also a distributed component, because if some of the water has evaporated, some of it is present in the gas phase. So we need to write down an equilibrium relationship for water also as an other distributed component. So for water, I'm just going to write down Rail's law, W for water, Y water, P is X water, P water sat. If it's a different liquid, then it would be water, it would be something else. Water is, or this liquid here is the dominant component, and whenever something is, whenever a liquid solution is mostly this component, actually the activity coefficient is roughly 1, and for the dominant component you have Rayleigh law valid. So typically if you do account for evaporation of the liquid that's used in the absorption process, you get to use Rayleigh's law for that. You don't have to worry about Henry's law constant or activity coefficients for that. That's just Rayleigh's law. So my point here is that I'm reminding us of some thermodynamics we're going to use. Certainly the component that's being absorbed is a distributed component. It's present both in the gas phase and the liquid phase because that's what we want. We want the liquid phase to pick some of it up. So we have to write down either Rayleigh's law or Henry's law for the component that we're absorbing. And that's where you stop if you do the simplest version. But if you also account for evaporation of the liquid, then that absorbing liquid is also a distributed component, and you have to write down an equilibrium relationship for the liquid that's doing the absorption also. So either you just have this equation alone and neglect the evaporation of water, or if you want to do the more complicated scenario where you account for evaporation of water, then you have to have both these equations, one of these and one of these. And so with that, I'll stop talking theory, and we'll cut to a worked example problem where we actually do the math and work out what happens in an absorption scenario.